Hey, good evening, Ray Hong and Siren. Welcome to O-level physics lesson on the topic on dynamics, the third topic for O-level physics. And today is Monday, 13th of March, which is also your school holiday. Okay, how's your school holiday so far? Okay, Ray Hong has a very good holiday. Siren, okay. All right. Okay, so let me show you all okay, this doesn't really apply to you all. Okay, this doesn't apply to your, but generally the topics are the correct, but there's a bit of shuffle here and there. Okay, so we are now at the green topic. Okay, so kinematics is the study of motion. Okay, the study of motion. So we are going to the third topic called dynamics. Okay, dynamics, we're going to study how force affect motion. Okay, I repeat again. Dynamics is actually a study of how force affect a motion. So in summary, dynamics is the topic of forces. Okay, forces. In primary school, you learn forces. Okay, in secondary school, we call it dynamics. Okay, so can you type out what is your understanding of dynamics? Okay, so can both of you tell me what is dynamics in your opinion? Okay, Ray Ho, well done. How about for Siren? Okay, incorrect, Siren. The study of motion is in the topic of kinematics. Okay, so the study of how a force affect motion is in the topic of dynamics. Is that clear, Siren? Okay, it's how a force affect motion. Okay, so let me show you what you need to know for this topic. Okay, so we are now at the topic of number 3. Okay, you need to know the type of forces. Okay, you need to know mass, weight, and gravitational field. Okay, you need to understand the Newton's laws of motion. And lastly, how resistive forces can affect motion. Okay, so these are the 4 things that I'm going to go through in this topic. Okay, this topic is quite big. Okay, so I will spend 2 lessons on this on the theory of this topic. Okay, so there are many types of forces. Okay, there are 2 types of forces. Number 1, contact forces, as well as non-contact forces. Okay, there's 2 types. So let me just highlight to you all. There are contact forces as well as non-contact forces. Okay, so you need to know what are the type of contact forces there are. So example, things like friction, air resistance, tension, normal force. Okay, these 4 are example of forces that there is contact. Okay, then there are non-contact forces. Okay, the 3 main one that you're going to learn will be gravitational force, okay, electrical force, as well as magnetic force. Okay, these 3, you don't need them to touch. There's no contact. Okay, but there's also a force acting on the thing. So before we start, okay, we also need to know there's 2 types of forces. But what is a force? Okay, in primary school, you learn that force is a push or a pull. Okay, so now we are going to categorize them further. Okay, we're going to categorize them into contact forces as well as non-contact force. Forces that is in contact as well as forces is not in contact. Okay, up to here. Any question for me? Up to here. Okay, so let me continue the talking about forces. Okay, so you also need to know that force. Okay, you need to use the understanding of force to explain. Okay, force can have effect on things. Okay, in primary school, you learn that. Okay, you learn a few things. Okay, force can actually make a stationary object to start moving. Okay, so you also learn that you can actually speed up or slow down objects. Okay, a force can do that. Okay, a force can also a force can also what it can do. Okay, a force can also make a moving of come to a rest. Means it's moving and then it can stop the object. Maybe just let me write down. Stop a moving object. Okay, and then you also have learned that the force can actually change direction of a moving object. Okay, then in primary school, there's one more thing that you also learn. Force can actually change the shape of an object, correct? Okay, so can you see in the first few of this? The first few, okay, what actually is force doing? A force is actually trying to change the motion. Okay, change the motion. Okay, what do I mean by change the motion? When an object is not moving and it remains not moving, is there a change in motion? Okay, can you tell me yes or no? When an object is moving and then it still remains not moving, is there any change in motion? Okay, hello Brian and Zachary. Can the four of you please on your camera? Hello, I'm asking you a question and why there's no response? Okay, so when it's not moving and then it remains not moving, there is no change in motion. Clear? How about when the object is moving at a constant speed in the same direction? Okay, for example, a car is moving forward at 10 meters per second. Okay, and it continues to remain at that speed in the same direction. Is there any change in motion? Is there any change in motion? Okay, so for both scenario, if the V is 0 and it still remains 0, there is no change in direction. Okay, and the direction of the V is the same. How about if the V is a value of n and then it remains the same n, the same value? In this case, I say 10 meters per second. But this n is 10 and it remains in the same direction. It remains in the same direction. Is there any change in motion? Okay, so in these two cases, there are no change in motion. Okay, when it's at rest, it remains at rest. There's no change in motion. When it's moving at a certain speed and then remain at a certain speed, there is also no change in direction. Is that clear? Okay, so the second one could be quite hard to understand. Okay, but I just want to let you all know. Okay, then in this scenario, when a thing is moving, and for continue to move in the same speed and the same direction, the motion remains the same. It is still moving at the same speed. Okay, so there's no change in motion. Are you clear about this? Okay, for a start, it may be hard to understand. Okay, but just remember, if it's not moving, there's no change in motion. If it's moving in the same speed and the same direction, there is also no change in motion. It is still moving at the same speed and direction. So there's no change. Is that clear? So when things is moving, it doesn't mean that there's a change in motion. It may be a change in position. Okay, but there's no change in motion. Is that clear? Okay, so for all the other 4 scenarios here, okay, you can say 5 lah. You want to split up the speed up and the slow down. Okay, then there will be 5 different scenario. Okay, so these 5 scenario actually change the motion of the object. Is that clear? Okay, so a force with a push or a pull that can actually have an effect, okay, in these 4 area or 5 area. And these 5 area are all a change in motion. The first one, when a stationary at rest, or the object at rest starts moving. Okay. Second one, when an object becomes faster or an object becomes slower. Okay, there is a change in motion. Okay, or when a moving object comes to a stop, there is a change in motion. And finally, the last one, a bit harder for us to understand when we're in Sec 3. Okay, the last one is when a moving object change direction. Okay, you need a force to make an object change direction. If not, you will not change direction. You will still move in the same direction in itself. Is that clear? So you need a force to make an object change its direction. Clear so far? Okay, so if an object is moving in a circle at a constant speed, okay, at a constant speed, is there a change in motion? Can you tell me by voting yes or no? Vote. Can you give me reaction yes or no? If an object is moving in a circle at a constant speed, is there any change in motion? Can you give me a yes reaction if you think there is a change in motion? Give me a no reaction if you think there's no change in motion. Okay, Brian say yes. How about the rest of you? Zachary say no. How about Rui Hong and Siren? Okay, Siren say there is a change and Rui Hong say no. Okay, let me revise again. The box here is there is no change in direction. If the speed is the same and the direction is the same, there is no change in motion. But in this case, even though the speed is the same, but the direction keep changing in the whole motion. So when the direction keep changing, there is a change in motion. Okay, Rui Hong and Zachary, are you clear now? Okay, good. Okay, so first of all, I already discussed what is a force. A force is a push or a pull. Then there's 2 types of forces: contact forces and non-contact forces. You need to be able to list them out. Okay, friction, air resistance, tension, and normal force. These 4 forces, any of you need me to explain any of these? Okay. Nobody need me to explain. So later on, then I try to explain. And then are you able to list out the 3 types of non-contact force? These 3 forces are the fundamental forces in this universe. Okay, gravitational, electrostatic, and magnetic force. Are you clear about this? Okay, all okay? Okay, so let me list down a few of the forces. Okay, friction, I will not talk about it. All of you know. Okay, air resistance is same as friction. Okay, so it's similar as friction is they are both resistive forces. Okay, these 2 forces are both resistive forces. Okay, so to me they are similar. They are not saying they are the same, but they are similar. Okay, tension. So for example, if what is a tension? Okay, I'll give an example. If I hang a ball on a string, okay, there is a tension. Okay, the ball is pulling the wire down. There is a tension on the wire. Okay, so this is a tension force. Okay, then what is a normal force? Okay, let me show you. If there's a table here, I put a book here. So the book has this thing called the weight. Correct? And because there is a weight, there is a force acting downwards. Okay, there's a force acting downwards. By right, there should be a change in motion. But the book remains there the same, right? The book does not move. Okay, why does that the book does not move? Because from the table to the book, there is this force called the normal force, which is equal and opposite, okay, to the weight of the book. Okay, okay. However, it will not be equal opposite. This normal force it will be always perpendicular to the surface. Okay, so for example, if I have a table that's slanted, okay, I got the book here. This is the weight. Okay, this is the weight. Okay, but the normal force will always be perpendicular to the table, to the surface. Okay, so if the book is not moving, can you see? If I were to draw a parallelogram, you remember the parallelogram thing? The book should actually move. But if the book is not moving, what is happening here? There is a third force, okay, called the frictional force here. Okay, that make the whole thing equal to net zero. Okay, so my point is the normal force is always acting perpendicular to the surface. Okay, so in this example, it's very clear that the normal force is not equal and opposite to the weight. Okay, it's not equal and opposite to the weight because it is the perpendicular to the surface. Okay, are you clear about this? Okay, if you clear, give me a yes reaction. Siren, are you okay? All right. Okay, so I have finished. Okay, hold on for a while. Okay, so I have mentioned about this. Okay, contact force means there is things that acting on it. Non-contact forces means there's nothing acting on it. Okay, there is a misunderstanding somewhere. Okay, let me explain to you. When we talk about non-contact force, okay, you may think that the objects are not touching each other. Okay, that is not true all the time. Okay, so a non-contact force can also be touching each other. I give an example of a magnetic force. So you have a magnet here, North Pole, and I have an iron nail down here. Okay, can you see here? The iron nail is touching the North Pole. Okay, so it's not true that all the non-contact forces has no contact. Okay, so for example, another example, the North Pole, in this case, they are not in contact. Yes, there is a these two are not in contact, but there is a force between them. However, when it is in contact, this magnetic force is still there, but it is in contact. So non-contact force doesn't mean that, it doesn't mean that things are not in contact. Is that clear? Okay, I give one more example. This is a human. When we are on the falling from the sky, okay, when falling from the sky, there is this force called the weight. Weight is the gravitational force. Clear? However, when we are standing on the ground, there is still weight. Okay, weight is the non-contact force. Okay, so it doesn't mean that when there's no contact, then it is non-contact force. A non-contact force can be in contact as well. Am I making you blur? Okay, so these two examples that I just mentioned, example 1 and example 2, are example of non-contact forces where the objects are touching each other. Are you all clear about this? If you are clear, give me a thumbs up. Thumbs up. Okay. Ryan, you're not clear. What part are you not clear about? Okay, so today we'll talk about these two. So we'll stop here. Okay, let me explain again. A gravitational force. So for example, you got Earth and the Moon. Okay, this is gravitational force. They are not in contact. Okay, this one you agree. Okay, we talk about magnetic force. You have a magnet and an iron nail. They are not in contact, but they are attracted to each other. Correct? Okay, they are not in contact, but they are attracted to each other. Okay, this part you are clear? Okay, these two examples are non-contact forces. Okay, they are non-contact forces. Okay, and they are not touching each other. This one you're clear. Next, what I'm trying to say is that non-contact force doesn't mean that they are not touching each other. Okay, I use a second example. You have the same big Earth. Let's say the Moon now is sitting on the Earth. Okay, they are still have a force. There's still force between them. So even though they are touching each other, okay, there are contact between each other. Okay, this gravitational force is still called a non-contact force. Understand now, friend? Okay, then for this, in this magnet example, the iron nail will be attracted to the magnet. So when it's attracted to the magnet, it is touching. Okay, they are both of them are touching, but there is still a magnetic force between them. Okay, so what I'm trying to say is that non-contact force may also be between two objects they are touching each other. Okay, is that clear? Brian is saying that so non-contact force is just a force that can act without contact. If that's the case, what you say is correct. Okay, it is a force that can act without contact, but when they are in contact, it doesn't mean that they are contact force. Okay, Brian, are you clear? All right. So any question for me before we go into the, okay, in your seniors learn this whole topic as topic 4, one big topic by itself. Okay, so your new syllabus, okay, the new syllabus is actually combine topic 3 and 4 under the topic of dynamics. Okay, so if you look at your own topics, you have less topic compared to your seniors. Okay, but actually you don't learn lesser thing because they just combine them together. Are you all clear about this? Okay, so I'm going to start talking about the mass, weight, and gravitational field. Okay, first of all, let me define what is a mass. Mass is the amount of matter in a body. Okay, can you all memorize that? What does this mean? Okay, what does this mean? This means that, there are how many matter in the body. So matter, you can actually think of it as things like particles, okay, or substance. You can replace the word matter in all this, or you can use the word atoms, okay, molecules. Okay, so basically, mass is the amount of this stuff, about amount of things in our body. Are you clear about this? Okay, so you can actually replace, but of course, when you define, you don't replace that. Okay, when you define, just use the word matter. Okay, matter or the word substance. Okay, but for your understanding, for the purpose of understanding, okay, the more matter there is in the body, the more atoms and molecules or substance there is inside the body. Is that clear? Okay, so the mass is a measure of how much particles or how much substance are there in the body. Okay, so, okay, but before I move on, let me go back to force again. Okay, the short form for force is capital F. Okay, the SI unit for force is the SI unit for force is Newton. Clear so far? Okay, the short form for mass is a small letter m. Okay, and the unit for mass is kg. Okay, what I'm going to share with you now is going to confuse you quite a bit, because it's something that you will find it weird. Okay, when I ask you, can you just tell me the answer in the chat? Can you tell me what is your weight? Can you type out your answer to me? When people ask you, what is your weight? Can you type out your answer to me? Then what will you say? Okay, share everybody. Okay, can you type out your answer? What is your weight? My question to you is, what is your weight? How will you answer me? Okay, type out in the chat your answer. And you shy, you give me a fake number. Just answer me the question. Okay, what is your weight? If I ask you what is your weight, how will you answer me? Yeah, just anyhow give a number. Zachary says 60 kg. Ray Hong says 60 kg. Steven says 55 kg. Okay, Brian, how about you? Brian says 110 kg. Okay. That is what you answer when people ask you what is your weight. Okay, but can you see down here? Mass. Okay, mass is using the unit kg. Okay? So what you are trying to tell me is not your weight. You're trying to tell me what is your mass. Is that clear? Okay, but of course, it'll start to get a bit confusing. Okay, so first of all, let me share with you the word kg, the unit kg refers to mass. Okay, 1 kg of mass is 1 kg of matter in the body. Okay, it's how much matter are there in the body. Are you clear about this? So if you on Earth have, let's say you have 10 atoms. If I move you into the outer space, you still have the same 10 atoms. Then if I move you to the moon, you still have the same 10 atoms. Is that clear? If I bring you to Jupiter, you still have the same 10 atoms. I bring you to far out in the space, you still have the same 10 atoms. So if your mass is 10 kg on Earth, it will still be 10 kg in space where there's no gravity. Or it will still be 10 kg on the moon 10 kg on the Sun, 10 kg on the Jupiter, 10 kg on Pluto, and so on. Your mass does not change. Is that clear? Okay, if you understand this, give me a yes reaction. Okay, so if you are 10 kg, your mass is the same everywhere you go, unless some of your mass is added to you or removed from you, then your mass change. If not, your mass does not change regardless of where you are. Okay, if you're on the moon, on the earth, your mass remains the same. Okay, so now that we learned about mass, can you all tell me how do we measure mass on Earth? Okay, how do we measure mass on Earth? Is a weighing machine a good way? Tell me yes or no. Okay, is a weighing machine the way to measure mass? Okay, tell me yes or no. Okay, so my answer to your is no. Okay, the answer is no. Okay, do not use a weighing machine or a weighing scale to measure mass. Okay, that is not correct. Okay, how do we measure mass? Okay, remember we talk about mass is the amount of matter in a body. Okay, so what we do to measure mass is to use this thing called balance. Okay, we use a balance to measure a mass. Have you seen before in those kind of Chinese medicine shop? Okay, where they actually compare two items here, and then when it actually balance, okay, when it's balanced, your mass of A will be the same as the mass of B. Okay, so if you have a model, okay, so you have a model mass, there's 1 kg here. Okay, you know that it's a calibrated and measured is 1 kg. And if you put something here and it balance, this something here A will also have the same mass. Okay, are you clear about this? Okay, so in this method, okay, wherever you go, whether you're on the moon, on the sun, on the earth, in outer space, to a certain extent, yes, you also work. Okay, why? Okay, if you're not moving, you also work because in outer space, there's also gravity. Okay, so basically, if you measure two things, you're just comparing two things, you're using a balance to compare the mass of two items, and that is how you determine your mass. Is that clear? Okay, you don't use a weighing scale, you don't use a weighing weighing machine, okay, or a scale. You know those Karang Guni, okay, they got this scale to measure your weight of your newspaper. Okay, those things measure the force acting on it. Okay, it doesn't measure how much mass your body has. Okay, the only way to accurately measure the mass is to compare using a balance. Are you clear about this? Okay, so we use a balance to measure a mass. Okay, so even you learn that you can use an electronic balance, right, to measure the mass of an item. You all do that in chemistry, right? Okay, you all actually take out a scoop of a chemical, okay, or powder, and then you put it on the electronic scale. Okay, that is not the proper way of measuring the mass. It happened to be, okay, you are using actually a force to actually measure the mass. Okay, so it may not be accurate because if you're on Mount Everest versus you're on Singapore versus you're deep underground, that machine will give you different reading for the same mass. Okay, so that is actually not the most perfect way of measuring mass. Okay, am I clear about this? Okay, am I clear about this? Okay. Okay, so mass is the amount of matter in the body. The short form for mass is m, small m. The SI unit for mass is kg. Is that clear? Okay, then we are going to talk about the next thing. The gravitational field and then the gravitational field strength. Okay, so all of you are now very clear about what the mass is how much things are there inside the body. Okay, the things can be metal, molecule, particle, substance. Just imagine that. Okay, when you actually mention, when you need to define, just use the word matter. Okay, if you use the word substance, it's fine. Okay, so you all now are very clear. Mass is the SI unit is kg. Okay, this is so very funny. Normally in all the SI unit, they don't have a prefix. But in this case, kg is the SI unit. Gram is not. Gram is not. Gram is actually a sub-unit of kg. Okay, so only kg is very different. Okay, so for distance, the SI unit for distance is meter. Okay, not kilometer. You know what I'm trying to say here? Okay, the SI unit for distance is meter and not kilometer. Okay, but the SI unit for mass is kilogram. Yes, the kilo actually means 10 to the power 3. Okay, but kilogram is your SI unit. Okay, you do a calculation based on kilogram as your base unit. Okay, not gram. Is that clear? Okay, so a bit of a thing that's not consistent. Okay, now next. The next definition that I want you to remember, that I want to remember 3 things. Okay, because now you're going to learn gravitational field. Okay, later on you're going to learn electrical field. And then lastly, you're going to learn magnetic field. Okay, so you're going to learn 3 types of field. So I'm going to teach you all the 3 types of field now. Okay, so that you just need to remember one thing. Okay, so can you see here? Gravitational field, electric field, and magnetic field. They all have the same word field. Is that clear? Okay, let me rewrite the whole thing. Okay, so gravitational field, we have electric field and magnetic field. Is that clear? Okay, so I'm going to expand what is the definition of these 3. Okay, so you must know that gravitational field, let me write down. Okay, what am I doing here is to show you that they are all the same thing. Okay, gravitational field is a region in which okay, so let me just write down the same thing here. So I just want you to remember the definition of these 3 are the same. Okay, so right now, what's the difference here? The difference are these few words: gravitational, electric, and magnetic. Okay, the rest of the word here are the same. So what are the same here? Let me share with you. Okay, so can you see over here? Gravitational field is a region in which a mass experience a force due to gravitational attraction. Okay, I need more space. So let me shift my stuff. Let me erase this. And then let me shift up. Okay, so I want you to remember. Okay, I want you to remember more things. Right from the start. Okay, but actually, what I want you to do is to remember just one thing. Okay, just one thing. Okay, so let me explain to you what do I mean. Okay, so gravitational field is a region in which a mass experience a force due to gravitational attraction. Clear about this so far? So what is electric field? Let me explain to you. Okay, so an electric field is also a region in which a electric charge experiences an electric force. Okay, you all see the similarity? Okay, so in a gravitational field is how a mass experiences a force. In an electric field is how an electrical charge experiences a force. Okay, how about for magnetic field? For magnetic field, what do you think is the definition? Okay, a magnetic field is a region in which a magnet or magnetic material experience a magnetic force. Okay, so I want you all to see here, even though there are three different fields, okay, but they are all the same meaning. You just need to change the word mass, okay, electric charge, and magnetic material. Okay, it's where it's a field, it's a region, it's a place where a mass experiences a gravitational force. Okay, electric field is a region where a charge experiences an electric force. Then magnetic field is a region in which a magnet experiences a magnetic force. Can you see this? How these three actually are very similar. You just need to change, okay, these three things with what the related stuff here. Okay, for gravitational, it deals with mass. The greater the mass, okay, like the sun, the greater the gravitational force. Okay, so the gravitational field will be greater. Okay, electric field is got to do with positive and negative charges. Whereas for magnetic field is where a magnet or a magnetic material experience a magnetic force. Okay, do I make myself clear about this? So I do not want you to remember three separate things differently. I want you to link them up, see that they are related, and basically just remember one time. And then just adjust the stuff here separately. Is that clear? Okay, if you understand what I'm trying to say, give me a yes reaction. Zachary, are you okay? All right, so allow me to continue. Okay, so all of you now know what is a gravitational field, and in extension, you also know what is electric field and magnetic field. And do you realize these three stuff are the non-contact forces? Okay, all these three stuff are related to the non-contact forces. Okay, related. Okay, so this is a gravitational field. It's a region in which a mass experiences a gravitational force. Okay, electric field is a region where a charge experiences an electrostatic force. And then the magnetic field is a region in which a magnetic material experiences a magnetic force. Okay, so these three are the fundamental forces of this universe. Okay, but they are related in definition. Just that for gravitational is talking about how a mass experiences a force. Electric field is where a charge can experience a force, and magnetic is where a place where a magnetic material experiences a force. And let me tie down further. When you experience a force, okay, remember I told you this topic, dynamic is how a force affect motion. Okay, you learn motion. In the last topic. So when a mass is in a gravitational field, you expect the mass to change its motion. Is that clear? Okay, if an electric charge is in an electric field, you expect the electric charge to change its motion. Okay, when you change the motion, okay, you can either stop moving, start moving. Okay, the five things that I'm going to mention. Speed up, slow down, and the last one, change direction. Is that clear? So when a mass experiences a force, the mass will actually have one of these five effects. Okay, when an electric charge experiences an electric force, the charge itself will actually experience one of these five effects. So when a magnetic material experiences a magnetic force, this magnetic material or the magnet will actually have one of these five reaction. Are you all clear about this? Okay, we are clear about this. Give me a clap reaction. Give me a clap reaction. Okay, thank you, Brian Ray Hong. Siren and Jackery, are you all okay? Jackery, are you all right? Okay, I'm actually moving very slow, but I want you to understand the idea. Okay, I do not want you to remember, to memorize. I just want you to understand, and then things will actually flow out naturally from your brain. All right, so far? Okay. Now, the next definition that we need to remember, which are going to help you understand, is this definition called, okay, we talked about gravitational field just now. Okay, we talked about gravitational field. Now we're going to add another word, gravitational field strength. Okay, field, there's no meaning to it. It's just a place where your mass experiences a force. Okay, and this force is called weight. Okay, so gravitational field strength is basically the amount of gravitational force per unit mass. Okay, gravitational force per unit mass. And this G, gravitational field strength, the symbol for that, the short form for that is G. So let me use the actual example to explain to you. G, gravitational field strength on Earth, is 10 Newton per kg. What does this mean? This means that on Earth, I have this object that has a mass of 1 kg. So on Earth, this 1 kg item will have a gravitational force of 10 Newton. Is that clear? Okay, so on Earth, every kg of mass will experience 10 Newton of gravitational force. Did I make myself clear? Now, I'll give another example. The G on the moon is about 1.6 Newton per kg. Okay, so on the moon, the same object, the same mass of 1 kg will only experience, or will only have a 1.6 Newton of gravitational force. Is that clear? Are you all clear about this so far? Okay, so basically, gravitational field strength tells you how much gravitational force is does the mass have per unit mass? Per unit mass means per kg of mass. Okay, so on Earth, every unit mass or every unit kg of mass mass will experience 10 Newton of gravitational force. Okay, on the moon, every kg or every unit mass will experience 1.6 Newton of gravitational force. Okay, so up to now, are you all clear about this? Are you all clear about this? Okay, if you are clear, give me a yes reaction. If you are not clear, give me a no reaction. Okay, thank you, Brian. Thank you, Siren. Ray Hong and Zachary, are you okay? Okay, thank you, Zachary. Ray Hong, are you there? All right. Okay, so I'm done with D. Now we are going to the last two very fast already. Okay, so we're going to the last two. Let me explain the last two to you all. Okay, so now you understand what is mass. You understand what's the meaning of gravitational field. You know what does gravitational field strength means. To tell you frankly, when I was your age, I never understand what is gravitational field or gravitational field strength. I just remember, I just memorize, okay? But I hope today I help you all understand the difference between these two and understand what's the meaning between these two. Okay, because when I was a student, I did not figure this out until when I'm older. Okay, so hopefully today I did help you all understand what's the meaning of gravitational field and what's the meaning of gravitational field strength. Is that okay? Now, we are going to, okay, the next thing, the one of the two formula that you need to remember is this formula called weight equal to mass times gravitational field strength. So basically, in short form, weight is a capital W, mass is a small m, G is this G, G is your gravitational field strength. Okay, so all of you need to know this. Okay, and then you know that G actually means on Earth is 10 Newton per kg. Okay, so does it make sense to you? Every kg of mass, you multiply by this value, will give you the weight. Does that make sense? Okay, I'll show you another, I'll show you the same example again. A 2 kg of mass, remember I told you on Earth, G is 10 Newton per kg. So if it's 2 kg, you actually have a 20 Newton of force, gravitational force acting downwards. Then if I were to use the formula W equal to mg, if my m is 2 and my g is 10, I got 20 Newton. Okay, does that make sense to you? Are you able to relate B to E together now? Are you able to relate all this together now? Okay, if you are able to relate and tie in B to E, give me a yes reaction. Okay, so let's go back to the misconception. If your mass is 2 kg, okay, if your mass is 2 kg, your weight will be 20 Newton. Okay, your weight is 20 Newton. Okay, let me just extend further. Some of you tell me. Okay, some of you tell me your mass is 60 kg. Can? Okay, that's your mass. Then what is your weight acting downwards towards Earth? Okay, so based on this formula, if your mass is 20 kg, okay, 60 kg, so now instead of 2 times 10, I change it to 60 kg times 10, I'll get 600 Newton. So my weight in this case will be 600 Newton. Is that clear? Okay, so let me continue explaining. So mass is the measure of amount of body, matter in the body. That is mass. Clear? Then what is weight? Weight actually is an example of a weight is a gravitational force. Clear so far? Weight is a gravitational force. So weight is a force. Mass is a amount of matter in the body. So when you step onto a weighing scale, it will show you 60 kg. What's happening here? Why does your weighing scale show you 60 kg? So this is a misconception in science, in physics. You don't say that your weight is 60 kg because weight is a force that is measured in Newton. Whereas mass is the amount of matter in the body that has a unit of kg. Okay, so why does your weighing machine shows you 60 kg? What is happening here? Okay, so if you were to stand on the weighing machine, you are actually applying force. You are pushing down on the weighing machine. So your weighing machine actually is measuring force. It's measuring your weight. Then they use this formula, W equal mg. They let G be 10. And then they actually recalculate your mass for you. Is that clear? Okay, but this is not an accurate way of measuring your mass. It's just assuming that at the point where you stand on it, your G is actually 10. Is that clear? And therefore you actually get a mass of 60 kg. What happened if you stand on the weighing scale? Then you fall down freely. So you're acting, your weight is acting on it, but your weighing scale no longer shows 60 kg, it will show you 0 kg. Why? Because both of you are on free fall. You are not exerting any force on the weighing machine because both of you are falling, so it shows 0 kg. So does this weighing machine actually effectively help you to measure your mass? Okay, the answer is no. If I bring the same weighing machine to the moon, it will not show you 60 kg. It will show you 10 kg. Is that clear? It will show you 10 kg. Why? Why does why does your weight become 10 kg now? Does it make sense? I already told you just now, mass is the same whether you're on Earth or a moon. But if you bring this same weighing machine up to the moon, your force acting on it is lesser, is 1/6 of your force on Earth. So instead of 60 kg, it only shows 10 kg. So does this actually reflect your weight, your mass? No, as well. Up to now, I know I'm actually quite confusing, but do you understand what I'm trying to say? Why a weighing machine is not the most accurate way to measure your mass, even though it tries to tell you that you are 60 kg. You understand this concept well? If you understand what I'm trying to say, give me a thumbs up. Ray Ho and Jackery, thank you. Brian and Siren, are you confused? Thank you, Siren. Brian, are you okay? All right. So up to now, any question for me? Okay, there's no question. So can you now tell me, now as a physics student or a scientist, now can you tell me, number one, type out in your chat, tell me what is your mass, and then tell me what is your weight. Assuming that G is equal to 10 Newton per kg. Can you do that now? Tell me what is your mass and then calculate your weight. Okay, can you type out what is your mass? I'll give you an example. Maybe that will make it easier for all of you. Okay. So let me give you an example what I expect. Let's say if my mass is 80 kg, for example. My weight is equal to mg. Okay, I want to see this. My m will be 80 kg multiplied by g, which is 10 Newton per kg. So my mass is 800 Newton. Okay, so can you do that and then type it out and show me? Ray Hong, can you write down the formula? I want to see W equal mg. Try again. Okay, Zachary, I want to see a formula as well. Your W should be capital. Okay, try that again. Your Newton should be capital as well. Okay, Zachary, well done. Ray Hong, well done. Ryan, can you show me the formula? Your W should be capital, not small. Okay, very good. All of you are okay. So I'm waiting for Ray Hong to adjust your answer. Okay, well done. Okay, now the last part today, I'm going to talk about the difference between mass and weight. Okay, so I'm going to talk about this and we will end the lesson slightly earlier today. And a clue, I want you all to actually listen carefully because my checkout question will be based on this. Okay, so we better listen carefully so that you know what I'm trying to tell you. Okay, what is the difference between mass and weight? I'm going to make it very detailed. So later in the checkout question, the answer, you should also give me very detailed. Okay, so I give you a warning already. Without warning, I give you a hint. Okay, I give you a hint already. Okay, so what is the difference between mass and weight? Okay, what's the difference between mass and weight? Ken? Okay, so the symbol is small m. The symbol is capital W. Clear? SI unit. This is kg. And whereas this is Newton. Okay, so far? Okay, what other difference between both of them? Okay, mass is a scalar. It's an amount, it's a amount of matter in the body. So to count the item, the count the matter is a scalar. Whereas weight has a direction. Okay, weight is a vector. Clear so far? Okay, so what is mass? Mass is the amount of matter in the body. Okay, how about for weight? What is actually weight? Okay, weight is the gravitational force exerted on the body. Is that clear? So that is the what? Okay, so for mass is fixed. Okay, wherever you go. Whereas for weight, okay, depends on the gravitational field strength. Okay, so for weight, it actually changes where you go. Whereas for mass, okay, it's actually fixed. Okay, what other things that is different? Okay, can you think of anything else? That's all I can think of. So there are five different differences, okay, between mass and weight. Is there any other difference? Okay, so are you clear about the differences between mass and weight? Okay, if you are clear, give me a yes reaction. And I shall, do you want me to continue or should I just end at this part? Okay, so give me a feedback in the chat. Enough for today or you want more? Tell me enough or more. Type in the chat, enough or more. Okay, I got one person that give me two answers so far. How about the last two? What's your vote? Enough or more? Enough or more? They quickly ask your vote also this so long. Okay, last one. Last one. Rui Hong, you have to decide. Because there is one vote for enough, one vote for more, and one vote for anything. So Rui Hong, what is your choice? Okay, Rui Hong say enough. Okay, before we go, let me share one more thing with you all. One more misconception that you all have been learned before. Okay, y'all, have you all heard about the Earth? If you're on if you're slightly above the Earth, okay, you say that you are actually weightless. Okay, this is incorrect. Okay, it is incorrect. When you're in space near the Earth, you are not weightless. Okay, you're not weightless. But you seems to experience weightlessness. You know why? Okay, so let me show you. Let me show you what's happening here. If let's say, for example, this is the distance between the Earth and you. Okay, and then this is the amount of weight, okay, or the amount of force between you and the Earth. Okay, it will come down like this. Okay, it will come down like this. Is that clear? So, no, even though you are infinitely far away from Earth, your weight will not be zero. But why is it that in the movie you see the astronaut falling, like floating in the air, like there's no weight? Okay, why is that so? Okay, it is not because there is no weight acting on the astronaut. Okay, that is wrong. Okay, when the astronaut experience weightlessness, okay, it is not because there's no weight, there's no gravitational force acting on it. Okay, that is incorrect. Okay, that's incorrect. Okay, so why do the astronaut experience weightlessness even though you are just slightly above the earth? Okay, if you are slightly above the earth, your weight shouldn't be much lesser until become negligible. Your weight is still very high. Okay, instead of 600 Newton, you could be 400 Newton. Okay, why is it still so high? Because you're not very far away from the earth. Okay, so your weight is still a big figure. But why does the astronaut experience weightlessness? Let me explain to you all why. I just want you to imagine you're on a lift. On a lift. Okay, on a lift. Suddenly, the string holding on to the lift snapped. So you and the lift start to fall at free fall. Okay, so when you're falling at free fall, are you experiencing weightlessness? Yes or no? Okay, so you're actually experiencing weightlessness, but you still have weight. You're still on Earth. Your weight is still the 600 Newton. Okay, but because you're falling at the free fall, okay, you feel like there's no weight. I'll give another example. Okay, we do go skydiving. When you jump out of the plane, when you're falling to the earth, you feel like there's no weight, correct? Okay, there will be also no weight. Okay, when you're skydiving, you also feel like there is a weightlessness. Is that clear? Okay, so hold on for a while. We are. Okay, so when you are on free fall, you are actually experiencing weightlessness, but you still have weight. Understand so far? Can you understand this concept? Okay, so why does the astronaut actually felt weightless in the space? Okay, so we have this Earth here. We call this the Earth. So astronaut is in this thing here. And you know that this thing is moving at an orbit. Clear so far? Okay, so if this thing is not moving, okay, if this your spacecraft is not moving, okay, can you see? Okay. Okay, so if your spacecraft is not moving, like this, if it's not moving, okay, it will fall down to the earth. Okay, because it's very near, there is actually gravitational force acting on it. So when it's falling down to the earth, okay, you'll be attracted, okay, and then you'll fall down to the earth. Okay, but however, in the spacecraft, it's actually moving in a circle, okay, and it's moving in this direction. And there's also a weight coming down. Okay, there's a force moving in this direction. Okay, so when your spacecraft is in the orbit, it is moving fast enough. Okay, the speed is fast enough that actually you are falling down. Okay, you're actually falling down. But because you are moving fast enough, you're actually ending up falling around the Earth. Okay, that's how the satellite, the spaceship actually move on the outside the Earth. They are actually falling around the Earth. So if their velocity is high enough, okay, if they are moving high enough, they will be actually falling around Earth. Okay, so I give another example. You are on the Earth. If you throw a stone, small speed, it will fall down like this. You increase the speed, it will fall down further. So you throw it at a speed that is high enough, you actually go around the Earth and then you come back. Understand what I'm trying to say? So that's what happened to the spacecraft orbiting the Earth. They are moving fast enough that they are now falling around the Earth. Just like the stone. If the stone is moving slowly, it will drop to the ground. But if it's moving fast enough, it will move so fast that it's still dropping. You'll drop around the curvature of the Earth. So you just drop around the Earth and come back at the same point. Then it becomes, the stone is now in orbit around the Earth. Is that clear? Is this information interesting? And because the astronaut is in the spacecraft that is falling around the Earth, okay, therefore it experiences weightlessness. Because you're falling, just like you're in the lift that is falling without the string, you experience weightlessness. Just like you're doing skydiving, okay, you're experiencing weightlessness. So for the astronaut in the spacecraft, they are actually falling, okay, falling around the Earth. So they are also experiencing weightlessness. Even though there is still weight, the astronaut still has weight. Okay, maybe not as high as on Earth, but they still have a high weight. Is that clear? Okay, do you understand what I'm saying so far? If you understand, if you like and if you think this fact is interesting, give me a yes reaction. If your school teacher has explained this before, give me a thumbs up. Okay, if you think that this is the first time you hear and then you understand it well, give me a yes reaction. Okay, so your school teacher have never mentioned this before. It's the first time you hear. Okay, so when you see the astronaut falling, okay, sorry, you see astronaut floating in the spacecraft, it's not because they have no weight. It's just because they are actually falling around the Earth. Okay, understand? Okay, so let me show you all these 5 differences again before I remove them. Okay, so the checkout question will be 3 questions. What are the 5 differences between mass and weight? 2, how much did you learn today? Okay, third question, how well did Mr. Chu teach today? Okay, so once you give me the answer for these 3 questions, I call your name, you may leave. Okay, Zachary, you may go. So Zachary share the answer to everyone. Okay, sorry, I was saying that Brian and Siren, you all both can go. Any question for me? Okay, Ray Hong, let me read your stuff. Ray Hong, today the rating is what, 2.8 and 3.9. Okay, I understand what you mean. Okay, Ray Hong, you may go today. Thank you so much. Okay, good night. Rest well. Okay, see you all when the school reopen.
Bye bye.